Excellent. Hello, everyone, and welcome to another webinar. As you come in, please introduce yourself on the chat. Just let us know where you're from, and we'll start in about 10 minutes, 10, 15 minutes. There you go. We have people coming in. Hello to Cape Town, Illinois, and Ontario, Canada. Very nice. All right, so we have people coming in from Argentina, Nebraska, India. Oh, how wonderful. Wow, one more minute to go until we start, and it's wonderful to see people coming from all over the world. South Africa, LA, Germany, Florida, New Jersey, Arizona, Argentina, Indonesia, Alaska, oh my goodness, Missouri, India, everybody's here, which is wonderful. Um, so let's leave it a couple of more minutes before we get started. Oh, wow. Oh, hello from Brazil. Hello, Brazil. Hi, Ale. Cool. It's actually impressive. It's we have one of our attendees saying it's 1 a.m. in Indonesia, and they are participating. They're here. I hope you're observing as well. Hi, India. Oh, how wonderful. 11:30 p.m. in Mumbai. Wow. Netherlands, the UK is here. Cool. Hello to Vermont. I hear it's nice and warm in there. Awesome. Hello, Maryland. Cool. So it's the top of the hour. Tom, do you think we should get started?
Yes, I think that's probably the best thing to do.
Wonderful. So hello, everyone. Good morning, good afternoon, good evening. Thank you so much for joining us. This is the 7th webinar of this series, and I'm joined here with Tom Calderwood, Erwin van Ballenhooy, and Jim Kay to talk about photoelectric photometry and try to understand one of the big enigmas in the sky, the night sky right now, Betelgeuse. First, I would like to acknowledge the Boyce Research Initiative and Education Foundation that is supporting this seminar. Boyce Astro provides online astronomy education, observatory resources, and research experience to students, student teams, and schools to learn how to perform observations, conduct research, and publish the results in scientific journals like the Journal of the AAVSO. They have been a partner, a really good friend of the AAVSO for years, and they are supporting this seminar. Also, I would like to acknowledge Attic Cameras that are also a sponsor. They manufacture a diverse range of quality astrophotographic cameras and accessories alongside with a range of free software to help you maximize the output of your equipment. So please visit their webpage for more information, even to look at free software there. As always, links to our sponsors can be found on your best post-webinar mail. So I would like to start with some housekeeping items. First, you have two little icons here for on your Zoom screen. One will help you access the chat, and this is where you're saying hello right now. So please keep the greetings coming. It's really great to see where you're all from. And the other one here that says Q&A, this is for you to ask questions. You can definitely ask questions during the presentation that are going to be addressed by our panelists a little bit later. Also, there is another icon here, a microphone icon that will help you deal with technical issues. Actually, if you click on that, you will see an audio setting link here. This is going to help you deal with any technical issues you might have during the webinar. We cannot help you with that. So with that in mind, I would like to invite Tom Calderwood now to share his screen and get us started. Tom, all yours.
Okay. Good morning, good evening, or afternoon, everyone. Welcome to episode 7 of the Observing Section seminars. My name is Tom Calderwood, and I will be talking about photoelectric photometry. We will discuss the history of PEP, why it still matters, how it is practiced at AAVSO, and last winter's excitement with a certain star in the constellation of Orion. Some of you may never have seen a photometer. Here is a simplified sketch. The key pieces are a sensor, a counter, an eyepiece, and a flip mirror. With the mirror down, the eyepiece is used to center the target. With the mirror up, light falls on the sensor, and a counter records the flux. We sample one star at a time, integrating on the star and then on the nearby sky. This may seem like a clumsy procedure, but it's how the foundations of modern photometry were laid. These men knew what they were doing. Here is one of my photometers on my telescope. The big red box at left is just a transformer repurposed as a counterweight. Here I am with my hand on the mirror knob, about to flip the mirror and start integrating. Okay, so much for introductions. Let's go back to the very beginning of the PEP story. PEP is based on the conversion of light into electricity. Albert Einstein explained the effect in his 1905 paper. And this, not relativity, is the work for which he got the Nobel Prize. Like photometers, cameras are photoelectric. The difference is that a camera has many, many pixels, while a photometer has only one. The practice of PEP is single channel photometry. PEP started years before AAVSO existed. Astronomers in Ireland and England experimented with crude photocells on very bright targets. Some of these men were actually amateurs. In the decades that followed, improved photocells became available, although none of these were very sensitive. Some results from that era can still be found in the AAVSO data system. Here is a variable star index entry based on 1915 data from Paul Guthnick in Germany. PEP took a huge leap forward with vacuum tube technology. This is the model 1P21 from Radio Corporation of America. It revolutionized photometry. The photomultiplier tube converts a photon into electrons, then creates a growing cascade of more electrons that can easily be detected. Here's a simple sketch of the process. One of the cameras on the Chandra X-ray Observatory works on a variation of this technique, so it's still used in modern instrumentation. After World War II, use of photomultipliers took off. Astronomer Gerald Cron wrote a how-to guide for the professional community and for amateurs. Up until this time, most photometry was done with photographic plates. Brightness was estimated by measuring the size of star images. Northern Hemisphere observers used a set of stars near Polaris as magnitude standards. The greater precision attained through photomultipliers revealed that the North Polar sequence wasn't very good and needed replacement. There followed one of the seminal papers of astronomy, courtesy of Harold Johnson, for whom the Johnson photometric system is named. Johnson and his partner Morgan used the 1P21 tube with 3 filters of colored glass to establish the UBV system. As professionals threw themselves into the new technology, amateurs were not idle. They started building their own photomultiplier instruments, and their efforts really expanded about 40 years ago. At that time, the International Amateur Professional Photoelectric Photometry Organization was formed, and the Center for Backyard Astrophysics also became active. IAPPP started out on the American East Coast and later set up a Western branch on the West Coast. And that Western branch eventually became Society for Astronomical Sciences. Also at that time, resources for small observatories and amateurs started becoming available. There were low budget publications like these, as well as slickly produced titles. And an off-the-shelf photometer hit the market. The box on right is the photometer head. It attached to this telescope, while the box to left registered the data. This unit had early problems, but eventually produced good results. As the semiconductor revolution gathered steam, a new kind of sensor became available. The photodiode was much cheaper than the photomultiplier and had some technical advantages. It was very compact, it didn't need high voltage, and it was rugged. A photomultiplier tube can be damaged just by exposing it to ambient light while it's energized. A diode doesn't care about that. There's also a joke about the photomultiplier tubes. If you put one on a perfectly flat, perfectly level table, it will roll off onto the floor. And the more expensive the tube, the faster it will roll. The light-emitting diode has a dual personality. If you pump electricity in, you get light. But if you pump light in, you get electricity. Around 1980, the Optech Corporation introduced its Model 3 solid-state stellar photometer, SSP. There had been two prior models, but this is the one that really succeeded. The integrated package contained the sensor, filters, and electronics. It slipped right into your focuser, and you could run it off an internal battery. Here it's shown attached to a Celestron 8. In later years, Optech came out with additional photometers. There was a second generation SSP3 with digital controls and a computer interface. There was a photomultiplier model that also became available as digital, and another diode-based photometer that operated in the near infrared bands of J and H. J and H are just to the red of I band. And here's an assortment of Optech photometers. The SSP3 at left is a generation 1, the original style model. The SSP5 and SSP4 are the digitized digital control models. These photometers found widespread use with amateurs and small observatories. But once electronic cameras became available and affordable, they largely fell into disuse. Okay, so why does PEP still matter? It certainly has drawbacks. The diode photometers have limited sensitivity. Running these Optech devices is a hands-on operation. Okay, a certain amount of automation is possible, but it's not straightforward. You can't do dozens of stars every night, and you won't get whizzy results at the push of a button. On the plus side, the SSPs are great on bright targets. A lot of the stars that we observe in the PEP group are magnitude 6 and brighter. These devices don't cost a lot. We get almost all of them on the used market, and they're much easier to use than imaging systems. I'll also point out that the SSP3 is almost indestructible. I've dropped mine onto concrete, and this is a great advantage for the beginner. The single pixel PEP instrument is much less complicated than a camera. You can quickly learn how to use it, and strictly speaking, you don't even need a computer at the telescope. I've used SSPs in workshops for high school students who had no prior experience with the equipment. In about 1 hour, I can get them basically competent with the photometer. I set them up in teams of 2. The first night, one drives the telescope while the other works the photometer. The next night, they switch. And in the daytime, I even have them reduce some of the data by hand with a calculator. And a final important advantage. The PEP observer does not need total darkness. I can only see a little bit of the Milky Way from my house, and I happen to live near a streetlight. The fixture does have a shield, but it's still a streetlight. I get good results nevertheless, and I can work during the full moon. So how about PEP in our esteemed association? There was a committee formed during the photomultiplier era, and the PEP observing section came into being around 1980. Dr. John Percy and PEP section head Howard Landis were major players in this. The group had its own postal newsletter to keep everyone informed. An early project was a study of small amplitude red variables, targets that are difficult for visual observers. And keep in mind, at this point in time, there are no CCDs available. Today, most of us use the SSP3 on telescopes of modest size, and there are a few SSP4 and SSP5 units active. Almost everyone has a go-to mount, though it's not strictly necessary if you have good slow motion controls. We work primarily in V and B bands, and the SSP5 can operate in U band. Here's the basic observing process. We visit the variable star 3 times and a check star once. All the visits bracketed by samples of the comparison star. We integrate 30 seconds on the star and 30 seconds on the sky. If you have good telescope controls, you can pull this off in about 15 minutes. Since we move the telescope from star to star, we don't need a comparison right next to the variable. For bright variables, this makes finding a good comparison much easier. However, since our variable and comparison may be significantly separated, we must worry about differential extinction. A comparison at a lower altitude than the variable suffers relatively more atmospheric absorption, and this makes the variable look artificially bright. We correct for this effect, and this is something that DSLR observers, who also can have their variable and their comparison separated by a lot, generally do not do this. This is one of the differences between the two techniques. We have a variety of packages for reducing data. On the AAVSO website, we have a tool that lets you do V-band. We have a spreadsheet that will do B, V, and I. Irwin, we thank for that. There is a commercial package that works with the digital versions of the photometers. And I have my own program, my own reduction program that lets me reduce data from any of our observers. This is the online tool. It's found in the WebObs menu on the main page of AAVSO. And this is our spreadsheet, or a little piece of our spreadsheet that we used for BVI. Okay, some of you may have heard that Betelgeuse got very faint last winter. There's a PEP story in that. Betelgeuse is the nearest red supergiant. It's expected to become a supernova before too much longer, that is, too much longer in astronomical time. It's a huge, unstable star. It's like a boiling pot. And it has made many atoms heavier than hydrogen and helium. Because it's so big and so close, we can actually photograph it. This is the famous pair of images from Miguel Montargis from the Very Large Telescope. Supposedly, even the Australian Aborigines knew that its brightness changed. There are two current periodic variations, just over a year and one of about 2,000 days. And visual observers going back to Herschel also recorded it. In 2018, a group of astronomers with a variety of big instruments organized a campaign on Betelgeuse in the month of March, known as the Month of Betelgeuse. They continued their work, but there was no one in the group supplying broadband photometry. And so PEP began to fill that void. Here are the PEP light curves, BV light curves over the last 2 years. Most of these data happen to be mine, but I want to get more observers involved this coming season. You can see the big dip in brightness that happened in February. What caused it? Theory number one is that the star cooled off and so was radiating less light, either cooled off in total or developed a large cool area on its surface. Another explanation is that those heavier elements that have been escaping from Betelgeuse condensed, formed solid grains called dust, and that dust obscured the star. Another idea was that the short and long-term variations just happened to line up perfectly to cause the great dimming. And I saw one theory in a popular web discussion forum that the dimming of the star was eclipsed by our own planet X. That one didn't go very far. In early December of 2019, Betelgeuse had broken through the faint limit and was clearly heading lower. Mobster Ed Geenan sent out a telegram to alert the community and graciously put my name on the notice as well. By late December, the story was in the newspapers and the visual observers went bananas, as you can see here. In early January, professionals gathered for the winter meeting of the American Astronomical Society. On January 8th, there was a special session devoted to Betelgeuse. And in the days before, I was getting mail from mobsters saying, "Tom, what's it doing? What's it doing?" Hoping to get the very latest data. The excitement in the run-up to the AAS meeting produced an AAVSO campaign. I had to chuckle at the request for time series data. From a year and a half's worth of smooth light curves, it was clear that nightly variation was really very small. Astronomers sometimes hope for phenomena that just aren't there. Betelgeuse got down to about magnitude 1.6 in V-band. Even at that, it was bright enough to overwhelm CCD cameras. The photodiode was the best tool for the photometry, and I'll show that. Here's the V-band data from all of the PEP observers. It's very well behaved. There are a few dubious points, but if you read the comments submitted with those points, you'll know why there was trouble those nights. Here I have overlaid the CCD light curve in green. You can see that it's not as good. Beginning in February, I added R and I bands, cousin R and I, to my own program. Again, the curves showed smooth variation. Two DSLR observers contributed Johnson Photometry, and they did well, although the data are noisier. I want to particularly call out Wolfgang Vollmann, VOL, who works in V-band. I think he's one of the best DSLR observers, and his photometry constitutes the bulk of AAVSO's light curve over the last several years. But now let's add the CCD observations to these light curves, and things are starting to deteriorate. A CCD, though wonderfully sensitive, is a hammer that's just too big for this nail. In the meantime, we were also collecting infrared data with the SSP4. Jerry Persha is the inventor of the SSP instruments, and he now observed from New Mexico. With the great dimming in B and V, questions arose about J and H. How much had they changed? Fortunately, we had a little JH data from the year before. Jerry's 2020 magnitudes were close to those, so there wasn't a major drop in the near infrared. Our recent JH data may figure into some research. When light bounces off of dust grains, it becomes partially polarized. This paper describes imaging of polarized light from Betelgeuse. A burst of new dust may cause an increase in polarized light, and they saw such an increase. However, the dust would also absorb light and then re-radiate it in the infrared. If new dust was absorbing a lot of visible light from Betelgeuse, we could expect a boost in the infrared light. But our infrared curves follow the optical curve going down, though not so dramatically, before rising again with B and V, along with B and V. I wrote to the lead author of this paper to tell him about our data, and he said he would get back to me after they did some modeling. So this may yet figure into more work. And I have been waiting weeks for this paper to go public. The lead author is Andrea Dupree, the head mobster. Her Hubble data show a shock wave going through the chromosphere of Betelgeuse. Such a shock is consistent with a big ejection of material that could have subsequently condensed into dust. Andrea graciously made me a co-author on this. Betelgeuse pretty much disappeared at the end of April, but that hasn't completely stopped photometry. NASA has been using the stereo probe of the sun to look at the star. What they've been doing is tilting the satellite a little bit so it can see Betelgeuse. The stereo data here is in red, and it shows a surprising early start to Betelgeuse getting dim for this cycle. They're also going to try to get photometry using a camera on the Mars rover. I suggested to Andrea that the New Horizons might also be available. It turns out that that satellite can't be used right now, but perhaps next year they can use it. There are more publications in the works, and we're starting to get some sketchy observations coming in. Everyone is excited to see what happens this season. I was attracted to PEP for the opportunity to do high quality work without the hassles of imaging systems, and I have no intention of switching to cameras. PEP offers a middle path in variable star observing. It's a step up from visual that still retains a personal connection with the stars. If you aspire to chasing faint targets with a camera, you can still benefit from an apprenticeship in PEP. I think of a lot of the trouble you see in CCD observations comes from people not really understanding the basics of photometry. PEP is an opportunity to learn. And it can be a special tool for education. I just discovered this paper where a photometer was used to watch a deep exoplanet of a bright star. They didn't discover the exoplanet, they were just watching it. And I'd like to share a brief quote. Participants can look through the telescope and see the target and comparison stars, then watch numbers displayed on the photometer. This allows participants to directly connect their star watching experience to the light curve. In this way, the transit can come to life as something real and immediate, rather than being understood abstractly and obscured behind layers of computer image analysis. The PEP homepage can be found with the other AAVSO observing sections. We certainly need observers below the equator. So if you're in Australia, New Zealand, South Africa, or South America, we'd love to hear from you. Also, there are photometers gathering dust all over the world. Ask around, you may find one that's available, even if you don't want to use it yourself. We have an observer's guide that covers not only photoelectric photometry, but some of the basics of photometry. In 4 weeks, we'll be running a class on photoelectric photometry, and there are still seats available. Finally, meet our mascot, the Count from Sesame Street. Thank you for joining us today.
Awesome. Thank you very much, Tom. This has been a very instructive, let me share my screen here, presentation. I would like to remind you all that this presentation and the following Q&A is going to be on our webpage, on our YouTube page. So subscribe and actually be able to attend it later. Also, please give us feedback through the survey that we're going to send to you. As Tom mentioned, there is a free choice course coming up September 14 about photoelectric photometry. So if you want to learn more, please join us, sign up. It is free for all. Please remember to renew your membership. We are counting on our members. And of course, if you can donate and help us promote this kind of work and improve all the tools that we're providing to our community, we really appreciate your donations. So with thanks again to Voice Astro and Attic Cameras, I would like to open the panel for questions. And I'm going to start with questions that are coming through. And the first one is, what does it cost to acquire the photometer, filters, etc., assuming you already have a telescope system? Irwin, perhaps, or Tom, Jen, Jim, whomever.
I don't know anything about prices because I have my photometer on loan from somebody else, the AAVSO actually. They once got a photometer offered and I'm using that one now. But I know that the filters are quite expensive. A few $100s, I believe they are. Perhaps Tom knows a bit more about the pricing, but they're not really cheap, especially if you have to import them to Europe from the United States. Makes them more expensive.
The last few photometers that I bought used, generation 1, I was able to get for about $200. The filters do cost money. However, if you're interested in this kind of work, you should contact us about the possibility of getting a loaner device. Because like I said, there are in fact lots of them sitting idle. If people are interested in joining the PEP group, we can try shaking the bushes to see if we can make any of them come out.
One thing is, if you do buy a used one, you might need to buy new filters. They generally it's generally needed after a period of time, depending how it's been stored. But to Tom's point, looks like we might be able to help with loaner photometers as well.
So is there a preferred source for use photometer? Just a follow-up question to the one we just asked. Could you find one on eBay?
That's where they tend to pop up either on eBay or Astromart.
Okay, so
Yeah,
go ahead.
Yeah, no, I've said I bought mine on eBay. You'll find that the prices vary quite a bit from reasonable to unreasonable. So just kind of check back.
Cool. Someone's asking if I have PEP, who should I contact to? Tom, I believe that there is a contact information on the PEP observing section page that goes to you, that email goes to you.
Yes.
And
Go to the PEP observing section page and you'll find a link that lets you contact me.
awesome. And from there, when it comes to filters, what size filters are you using?
The filters are only a ½ inch in diameter. They fit into a custom slider. These are not the 1 1/4 inch filters that you use with CCD cameras.
It's good to know. Now, can someone build their own photometric photometer if they're familiar with electronics?
Yes.
So how can I find more information, Jim?
Well, certainly if someone's interested in that, then, contact Tom, myself. You certainly can do it. It's a fun project. I haven't done it myself, but I have some parts available that I might be willing to donate to somebody if they want to do it. The mechanics of it, the flip mirror and the nose piece for the telescope, it's great if you can use an old SSP device because that saves you a lot of time. And I think we could probably help someone out if they're interested.
Cool. So now we're talking about technical aspects of SSP. How faint will the SSP3 photometer work on a 10-inch telescope? Erwin?
Actually work on a 10-inch telescope. And most of my targets are quite bright. I go to the stars I observe around 6 magnitude. It's fainter than that, but then I get still quite good accuracy up to about 5,000 of a magnitude. For fun, I also tried the star X Cancri. It's a very red star, and I tried it with a blue filter once, and then I got into the 9 magnitude region, but that is really very inaccurate. So I think you should limit to 7.5 with a 10-inch telescope.
Now, does the photometer, Tom? Does the photometer need to be cooled?
No, it does not. It don't require a cooling system.
That is convenient to let it cool down to the ambient temperature. Then works better.
So can you talk a little bit about calibrations that need to be taken, how you observe? I mean, do you need darks and flats and biases like CCD? How do you focus the photometer? Can you elaborate a little bit more on the technique?
Tom, do you want to answer it? Do you want me to?
Jim, go ahead.
Yeah, so the basic observation technique, you're measuring the target star. So you put the photometer on there, measure the counts. You'll measure the sky and subtract that from the star. So you're essentially correcting for the sky brightness, right? So you do that automatically. I mean, you make 2 measurements. You do the same on the comparison star. And that's your basic observational sequence. We also do a check star. And the reason we do a check star is in case our comparison, unbeknownst to us, is variable. So that's the basic sequence. And then we also do And this is an interesting process. We also do a correction. Ideally, all of our instruments would be identical, all our filters would be identical, but that's not true. So the response of my system to color and Tom's system to color is a little bit different. So we've also identified these pairs of stars that are very close together, one of which is red and one of which is blue. And we have a calibration sequence that we like to do about once a season, where we measure those stars and we're able to calculate coefficients that we use to reduce our data to a standard system. As part of this PEP course coming up, we'll go through all of that. But in the interim, you don't have to do that. If you just do the basic measurements, we have programs that will go ahead and do the reduction. And if you do these measurements on the red-blue stars, we also have programs that will do the reductions and give you your coefficients. I don't know if you wanted to add anything, either Tom or Erwin.
Can I add something, Jim?
Yeah.
I think we once also did a study with one star, Rokas, and all people who are doing this kind of photometry were imaging this, the same target on the same day. And we looked at the consistency. And I think we also published a paper about this in the journal of the AAVSO. And the consistency was quite good, I believe.
Yeah, I know also Tom and I did some comparisons of consistency. And with the corrections, Tom, we were below, or correct me if I'm wrong, but we were better than 1/100th of a magnitude, if I recall that. Is that also what you remember?
Something
We
like
got,
that.
yeah, we were able to get different observers to agree very closely on the measured magnitudes. I don't remember the exact numbers offhand.
It was within that range. So one thing is that PEP done carefully seems to reduce very well to a standard system. And that allows us to use different observers to create a light curve where we get consistent data.
Ooh. So early on, you mentioned that you're subtracting sky from both your star and your comparison. That means that PEP observations can be acquired even under light polluted skies, correct?
Yes, that's right, because you correct for this sky brightness.
Wonderful, wonderful.
You can get best results in hazy skies, by the way.
Why is that?
The atmosphere is more quiet then, so there's more consistency in the measurements.
Awesome. It's good to know. So a question here, should data with an error greater than 0.02 be reported of the unit's magnitude? So
I didn't talk much about the precision we get with the photometers.
Mm-hmm.
A 20 millimag uncertainty is really quite large. You know, I consider good photometry to have a uncertainty of 5 millimags or less. If I'm over 15 millimags, then I tend not to submit the data, just because it's so far different in quality from what I usually get.
Okay.
You could still report it, but then you should post also a remark in the observations to specify why it's so off the measurement. Why there's such a big error in the measurement.
Cool. Tom, you mentioned that a computer is not strictly necessary. How would it help?
Okay, if let me take the screen back again. Stella, can I have the screen? Okay, there we go.
Yes.
So the big advantage of the computer is that it records the data for you automatically. You don't have to write it down yourself. It's also a big help when you're doing with really bright stars. You can see that little 4-digit counter. I mean, it only goes up to 99999, 9999, whatever. And so when you have larger numbers, it becomes very helpful to have the computer. And the Generation 2 photometers have the computer interface for an RS-232. I actually built myself a little Arduino computer. The older photometers have a pulse output. And actually the newer photometers have it too, if you know where to look for it. And you're handy with a soldering iron. But I use this little computer to collect my data. It's a really handy device. It writes the information onto an SD card. So if you're up for this kind of project, or if you have a Generation 2 photometer, the computer is a definite help.
Awesome. Thank you, Tom. So let me go back to sharing my screen, and we're going to go to more questions, one of which is, what are the best type of telescopes to use with the photoelectric photometer? They're asking, would a Celestron Edge 9.25 work out okay? Do you need an Altaz? How does that work?
Okay, you almost certainly want a Cassegrain telescope, just for starters. That's the key. On a Newtonian, if you put it in the Newtonian eyepiece, the photometer would be swinging all over the sky as you move the telescope. Be very inconvenient to use. As far as the actual type of optics, it doesn't matter much. We are only looking at the very center of the field of view. We don't care about what's happening off axis. And this, in fact, is one of the reasons why you can use an altitude azimuth mount, because we don't care about field rotation. So really, you don't need fancy optics to do this. As long as you get a decent image on the optical axis, you will be fine.
Can I add to this, Tom?
Sure.
This being said, that alt-azimuth mount is very convenient for this kind of work. My personal experience is that the standard go-to mounts of Meade and Celestron are very often not, the pointing accuracy is not enough to keep the target 30 seconds in the center of the image. So I changed myself to another mount, but the standard mount of Meade didn't work for me. So that's why I changed to another mount.
Jim, any comments?
No, I think I would just reinforce what both Tom and Erwin said. Typically, when we do the integrations, we do it in a set of 3 10-second integrations. So you want a mount that can keep the star centered in the aperture for that period of time. Mm-hmm. And the aperture will depend upon your scope's focal length. But generally, most of the mounts, I know the ones I've used, can manage it for the 10 seconds that you need to get a decent set of data. But obviously, then if you have to recenter it for the next integration, it starts to take more time. So although you can get by with a mount that doesn't track as well, you do save some time and frustration if you do have better tracking.
Actually, speaking of tracking, we have a question here about technique. What kind of technique do you use to find your target star? And if your target stars are bright enough, do you actually need guiding or tracking? Jean, since you started talking about that,
yeah,
please...
I found you don't need guiding. Most of the time for the 10 seconds and for most scopes, the apertures, you don't need guiding. So you just basically center the star in the reticle, go ahead and do your 10-second integration. If you're confident enough, you can do your 3 10-second integrations without looking again. and you're good to go. So generally, you don't need to track on the star. And Erwin or Tom, you can comment too, but I don't think either of you track on the star either, do you?
No, and you would need an auxiliary telescope to do the guiding, because there's no way to hook a guider to the photometer itself.
Right, but in our experience, it's not been needed.
No.
So pretty much, Tom, you've used a variety of go-to mounts and managed to make them all work, is what I know, although I know a couple of them you've had to, play around.
Right, they all, I mean, the various mounts, I mean, let's face it, folks, we all have been buying consumer grade equipment for the most part. Most of us are buying consumer grade equipment, and it's not, they don't track perfectly, they don't point perfectly. As far as finding the target, I'm just using a Celestron Nexstar mount, and the star I want to see is always in the field of view of the eyepiece somewhere after a go-to operation. So there's no difficulty in finding the star.
So how do you select your targets, and how do you select your comparisons and your check stars?
We actually have a list. We want everyone to use the same comparison stars. Mm-hmm. So there's a list of, I don't want to say approved, but
appropriate,
common PEP targets. That doesn't stop people from choosing their own targets and their own comparison stars. Yeah, in which case you would use the variable star plotter to find comparisons. But
we really encourage extremely strongly that you use the standard comparison list, unless it's a special observation campaign. Mm-hmm. And Tom, you can comment on this, but it just makes it easier for our data to be intercompared, and it makes the light. Right,
we have a, sorry.
Yeah, no, go ahead. Then when you do the light curve, it's all based on the same comparison star, and that tends to give you cleaner data. But go ahead, Tom.
For JH on Betelgeuse, we have an observer in New Zealand, and he cannot easily see the same comparison stars as those of us in the Northern Hemisphere. So inevitably we wind up with a divergence in our comparisons. But that's, we do that when we have to.
So where can we find that list comparison stars? It's on the PEP observing section page, I assume?
Right, there's a list of targeted comparison stars on the PEP web pages.
Wonderful, wonderful. Now, a little bit more technical question. Can you integrate for 60 seconds if you can track for 60 seconds? How long does each reading take? How fast can you add readings to the integration?
Well, you can integrate for as long as you like. 30 seconds, the benefit of a 30-second integration is that it beats down the effect of scintillation. You really don't want to integrate for less than 30 seconds. But if you want to go longer, there's nothing to stop you from doing it.
You will get a better signal to noise ratio with a longer integration, but the sweet spot seems to be around 30 seconds has been our experience. The gain you get by doing it longer doesn't usually justify the extra time, the tracking accuracy, and any changes in the atmosphere that occurs during that time. So kind of that's where the 30 seconds has kind of come from practical experience on those types of trade-offs.
How long is the readout time?
Readout time is 0.
Yeah, a lot less than 30 seconds.
Okay, so that is wonderful. Here is what is more important when choosing a telescope, aperture or f ratio or both? I would assume that has to do with PEP specifically.
Well, you generally want at least 8 inches of aperture. And if you want to work in the B band, the photometer is not as sensitive in B, then you really want about 10. There's no need to go to giant instruments. We're looking at bright stars. So, you only need a modest telescope, but you do want generally at least 8 inches of aperture.
And I'd say the F ratio, since we're not worried about the quality of the image, the F ratio will determine your aperture in degrees. And so it really comes back to tracking. So if you get to where you've made your aperture really small in terms of degrees, you're going to need a more accurate tracking mount. So again, as Tom said, most of us is commercial gear. So, standard Smith Cassegrains, anywhere between F8 and F11 tends to be what most of us use.
A question that has to do with technique again. You mentioned that you're going back and forth between stars. Why do you do that?
Okay, Stella, why don't you give me the screen again and I can go into this.
Okay. All yours.
All right. So, if you're using a camera, you just take one picture. Here we are taking, you might say, multiple pictures of the star, going back and forth, back and forth. And this has to do with the data tech, with the technology. There are two kinds of photoelectric photometry. You may have heard of pulse counting or photon counting. That's what you do with the photomultiplier for the most part. There is also direct current photometry. And the optic photometers are direct current photometers. When a photon comes in, you basically get a little dollop of electricity out of the electronics. And there are two options. You can count each little burst of electricity, or you can measure the current over time. Those guys back in Ireland and England, they actually used a meter. Early photometrists used a meter to record the amount of electricity coming out of the photometer. The photomultiplier gives a really strong burst when a photon comes in. The burst is sent through a discriminator circuit that tries to filter out noise and produces this nice clean pulse to give to a counter. And you get Poisson statistics out of this, just like the counts you get on a CCD camera. But in DC photometry, you're actually measuring the current coming out of the diode or whatever your sensor is. They originally, they used to do this with a strip chart recorder, and taking a measurement was called a deflection. As the little needle moved, it deflected. So this is how the optic electronics are set up. The photodiode generates a tiny current, really, that is fed into an op-amp amplifier circuit that converts the current into a voltage. The voltage, in turn, drives a voltage-controlled oscillator, otherwise known as a voltage-to-frequency converter. The oscillator produces a pulse train that drives the counter. It's really not a Rube Goldberg setup. Most of the electronics are very straightforward. The oscillator is the weak link in the system. However, if you use it properly, it is tremendously linear. I'm actually working on a project on the star Vega, which is magnitude 0, and I'm using a comparison star that's near magnitude 5. So as odd as this little electronic arrangement may seem, it actually works quite well. The difference is the counts we get out of the optic unit after it goes through all the electronics are no longer Poisson. And so we do 3 separate measurements and average those and get a Gaussian uncertainty. And so that's why we're doing the back and forth, back and forth. It's the same story as if you had taken your CCD and taken multiple exposures, averaged them together, and taken a Gaussian.
So just to comment a little bit on that too, we'll do comparison, target, comparison, target, comparison, target, comparison. And so we also have a data quality check because we can look at the magnitudes that we get for the comparison stars that bracket the measurement that we took for the target star. And so if your comparison star in your first reading and your comparison star in your second reading are similar, you can feel pretty comfortable that the sky conditions didn't change, that your instrument's working well. And that gives you real confidence that the data is valid. So that sequence helps do data validity as well as just the actual measurement.
Jim,
Yeah, the mascot, watch the counts. That's what you need to do when you're at the telescope. Watch those counts. Look at the counts of your comparison star and make sure that they stay just about the same over the course of the observation.
very nice. I think that now we all got the count. Because I was a little bit confused, to be honest. So a follow-up question, actually very similar when it comes to observing. How do you check for sky backgrounds? Do you have to go to a dark space without stars? How do you do that?
You do, but the nice thing is we're measuring bright stars. So what most of us do is offset it from the star, several way outside the reticle of measurement, and we just look for a dark space. And that typically works pretty well. And the other thing is you're doing it a number of times, and so you also look at the sky brightness, and you'll know if you hit something that's not the same darkness as the rest, you might want to take a look and say, hey, was there really a star in there? I haven't found that to really be a problem. It's been easy just visually to pick a dark space, and it's worked great. I don't know if Tom or Erwin have a comment on that.
However, when you have a very bright star, it is more convenient to look for a dark spot outside the field of view of the eyepiece, so that the bright star is not in the field of the eyepiece anymore. And it works better. The light pollution of the star might be causing problems.
Right, so you want to move far enough away from the target that it's not letting any light from the target in, which if you have scattering and things like that could occur. So absolutely true.
Yeah. Another question we have here, can you replace the eyepiece with an electronic eyepiece or planetary astronomy camera for centering the PET for people who can't do the necessary contortions to look through the eyepiece or of an equatorial mounted telescope?
The answer is yes, it has been done. I've actually, I'm a new observer who is starting up in PEP who plans to do exactly that. As that project proceeds, I am hoping that we can write up a kind of standard procedure for how it can be done.
Wonderful. What is the angular acceptance of the photodiode?
Do either of you want to answer? Do you want me to take a shot at it, or?
Go ahead, Jim.
It's going to depend on the F ratio of your telescope. For mine, it's about 1 arc minute. But it'll depend on your system.
Erwin, comment?
I never checked it, but it's similar what Jim said. It's about 1 arc minute. I think in my case even a bit less. The time.
Good time. A general question. Betelgeuse was the star of the year, and we will all want to know what's going to happen next. Are there any favorite star of yours? Is it personal preference that you would like to have more hands on deck, more observers to observe, and you would like to advertise right now? Erwin, let me start with you.
When I started to do PEP observing, Epsilon Auriga was my favorite.
Mm-hmm.
I wanted to follow this star in a very accurate way towards the minimum and afterwards. Of
Mm-hmm.
course, that's not very interesting anymore, not doing much, only the slow pulsations now and then. But myself, I have a preference for yellow hypergiants. There are not too many of them, but they are very bright, or even though they're very far away, they still stay bright. And when it's bright, it's about 5 or 6 magnitude, so it's very easy target for our equipment.
Mm.
And I started doing those stars upon request of a professional astronomer, and it's using my data now for publications as well. So that keeps me focused on the targets, because he wants years and years of data. And that's something that professional astronomers don't have time for, to produce years and years of data of the same star. So that's something amateurs really can step up into and do a lot of things in this field, because sometimes they want really years and years of data.
Jim?
I have to say I generally defer to Tom, which has generally been a good policy, because he seems to be tied in with a lot of campaigns by professionals that ask. And then I have a couple that I like to do just because they were my first stars, right? So you kind of try to follow them, like WBOO and ROCAS, but more of the science stuff, I tend to follow Tom's lead on that. I'll definitely say that.
So Tom?
Well, what I'm hoping to generate interest for, I've been drawing up a list of neglected bright red supergiants. And I've been following, I don't know, maybe 5 of them so far this summer in the north. And so I'll want to draw up interest for those stars. One of them is Xi Cygnus, otherwise known as NSV 13518. But Epsilon Pegasus. There are a couple of interesting red supergiants in Lacerta, V424 and V412. I'm also following Zeta Cepheus and V381 Cepheus. So, follow up on what all these other red supergiants are doing. I cannot see Antares myself. I have a poor southern horizon. So Antares is actually an important target. And there's also another interesting red supergiant in that area, BM Scorpius.
Excellent. So for Southern Hemisphere observers, perhaps we can actually come up with a list where they can follow interesting stars, right?
Yes.
That would be wonderful. So we covered all the questions from our list, and thank you to all our participants. We have more than 80 participants here. So we thank everyone for participating. Most of the questions had to do with technique of observing. So I would like to encourage those who are interested in diving in a little bit more to take the choice course. It's coming up in about a month from now. So I would like to close with one last question. Is Betelgeuse going to explode this season? I had to ask, I had to ask.
Would be fun.
Nobody. Nobody knows. I would just, you know, it's interesting that Betelgeuse is already getting faint earlier in its, I mean, Betelgeuse goes right now in about a 420-day cycle. And this latest cycle looks as though it might be starting early. So, you know, again, everyone's interested to know what will happen. I just want to mention that I encourage people who have questions to contact me. Use the contact information on the web page for the PEP section. I will be glad to talk to you.
Wonderful. And also let's remind everyone that we have a very active forum on PEP. So if they have any questions, they can actually ask through the forum. And with that, I would like to thank you all again, Tom Calderwood, Jim Kay, Erwin Ballenhooy, for a very interesting presentation and discussion. I would like to thank all of you who are attending. Good morning, good evening, good afternoon, whatever time zone it is. Keep looking up, keep observing, and please stay safe. And with that, I will bid you goodbye and see you next Saturday with spectroscopy. So bye, everyone, and thanks for joining us.
Take care.
Take care. Bye.